Hi, it's time for a chime slash transformer video. So this is a NuTone K model chime. This one in particular is from the mid-1950s, probably 1954, 1955. This belongs to one of our customers who sent it in for it to be repaired. And it's all been repaired and rebuilt and serviced, and now it works just like when it was brand new. For this customer, this chime originally was in her grandma's house. When they sold the house, they took it out and she got to have it, and she wants to put it in her house, and it hadn't worked in a long time, and that's why we repaired it. One of the things that she doesn't have for it is she doesn't have a low voltage transformer to power it with, and so she needs some kind of transformer to put in her house so it'll work properly. Transformers for K model chimes are unusual because back in the day these were powered by NuTone 20 volt transformers. And 20 volt transformers don't really exist much anymore nowadays. Those types of transformers are called class 2 transformers for dry locations, which mean they can be mounted onto an electrical box in your garage or utility room or someplace like that, and the low voltage wires connect onto the front and the 110 wires are inside the electrical junction box, and they can be out in the open where people are around because they're safe. Nobody makes 20 volt class 2 transformers anymore. The closest you can get nowadays, generally speaking, are 16 volt transformers, which are too low, or 24 volt transformers that are too high. The voltage is too high. And the reason that they're too high is inherent in the way transformers operate. How much voltage a transformer puts out is directly related to how much voltage is being put into it. Back in the day, back when this was new, in the US, our line voltage was somewhere around 115 to 120 volts. In some rural locations, it could be lower than that. There's actually NuTone service bulletins where they talk about what to do with intercoms and door chimes in rural areas where your voltage might be 105 or 108 or something like that, and sometimes that can affect how the product works. The more voltage in, the more voltage out. Also, voltage rating on transformers are under their maximum load. Now, this part gets a little complicated, and I'm not going to do a whiteboard on this because I've done it before, and there'll be a bunch of pop-up things that show up for other videos if you want more background. Transformers have two ratings. They have the voltage and they have the power output, which is watts, and I prefer watts, or volt amps, which is VA. That's a more modern measurement. Watts is easier for people to understand. The original NuTone transformer that came with this was rated at 20 volts at 20 watts. So the amount of power that was available in the transformer was 20 watts. Think about it like a 20 watt light bulb in comparison to, say, a 100 watt light bulb, which is a lot brighter. It only has 20 watts of power available. If you connect a device to it that wants more than 20 watts, the voltage will suddenly drop way low because the transformer can't keep up any longer. Now, if you took an original NuTone 20 volt 20 watt transformer and wired it up, and you use your meter and you measure it, what you're going to get out of the transformer is going to be around 22 volts or so, because that's a free running transformer. Nothing is connected to it. It's just sitting there running, and it's supplying a little more. But if you connect a device to it that's going to use the precise 20 watts that are available, the voltage out of the transformer is going to drop down a couple volts because it's now under load. And that's where the problem with using a 24 volt transformer comes in, because a 24 volt transformer in today's world, where in some parts of the country you might have line voltage into your house, instead of 120, you could be anywhere from 125. I've talked to people that have as much as like 128 or 130, which is way high, but that's what's happening to our US power grid because of the demand and the lack of infrastructure improvements. They keep jacking up the voltage to everyone's house, which is hard on a lot of products. So a 24 volt transformer is going to put out 26, maybe as much as 26.5 volts, and that's way too many volts for a chime like this. The motor specifically is a 20 volt motor, and that's what it was designed to run on. What we've done in the past, and I have videos that show how to do this, again there'll be another pop-up thing, is we have built what I call transformer appliances for people. While you can't buy a self-contained class 2 transformer that you can mount on your garage wall in 20 volts, you can buy something like this. This is one of the ones that belongs to the shop here. This is a 20 volt transformer, but this is a chassis mounted transformer. It's designed really to be installed in some kind of product, and then it's all encased in the product so it's safe, because on this side there's all these electrical connections, and I have it on a power cord because we plug it in, and we have these jumpers to make the right voltage, and these are the two wires that the 20 volts comes out of. This is a good solution sometimes, but the problem with this is, while the transformer itself is not hugely expensive, it's not a class 2 transformer. You can't mount this on a wall in your garage because you have all these exposed connection, and some 8-year-old's going to bounce into it playing in the garage and get shocked and get hurt, and that's not good. So what we do is we take transformers like this, up until now, and we build them into encased plastic electrical boxes, and we put terminals to put the wires and places for wires to connect on the outside, and we put a fuse and a cable to wire it into the electrical system, and it's all very elaborate, and then you close it up with the cover, and you can mount that on the wall of your garage, and it's perfectly safe and acceptable. The problem with that is that's expensive, because there's lots of parts and pieces that you have to buy to do that, and it takes anywhere from an hour to an hour and a half to build one sometimes, depending on what type you're building, and the cost to do all of that runs up really fast, so it becomes somewhat unreasonable for people because it's just too much money to spend so you can have grandma's doorbell ring. So recently I had an idea. We always have a lot of ideas around here. Sometimes they're good, sometimes they're not. I started searching around for a solution for this customer in particular because she's not going to be able to afford a transformer appliance. It's just too much money. Getting this fixed was enough, but that would have pushed it over the top. What I found this. Pay close attention. This is from a company called MG Electronics, or I guess it's MG Electronics going this way. This is a standard company that makes a lot of different types of transformers. Primarily they're used in things like security systems and gate operator systems, and they make a lot of different kind of transformers. And actually we stock a couple of these in a different voltage, in a 16 volt version, because we have some housing subdivisions in this area that use plug-in transformers for their NuTone intercom systems, because that's what the installing company did, and sometimes they blow out, and we'll talk about that in a second, and so we keep a couple around. So I was searching around and I found this transformer. This is a model MGT1850, and this will work for this chime. And as you can see down here, it says 18 volts this way. 18 volts AC class 2 transformer. So what is this? Well, this is, and if any of you have like a security system or something like that in your house, you'll probably recognize this. This is your standard sort of plastic cased, some people call them wall warts, plug-in low voltage transformer. It's got your plug-in connections on this side, you got your two electrical connections and a ground. It's got a screw here that screws into the hole where the screw plate would go, because this is fairly heavy so it doesn't fall out like this because it weighs so much. And it's got output connections here. Now if you're really paying attention, you might be thinking, well, you said that this is a 20 volt transformer and this is an 18 volt transformer. How does that work? Okay, so you have to remember what I talked about. An 18 volt transformer, free running like this, you plug this into the wall and you measure on the terminals here, what you're going to get out of it is about 20 volts. Then, if you really were paying attention, you might remember the part where I talked about how the 20 volts that come out of the transformer is the free running voltage, because no device is connected to it. And when you connect the device that draws power from the transformer, the voltage output will drop. Well, I had an idea of how to overcome this and make a more reasonably cost alternative for this customer. So this is an 18 volt transformer, but it's rated at 50 watts. The original transformer was 20 volts at 20 watts. This is 18 volts at 50 watts. So it's 1.5 times more watts than this had. This has big capacity. Remember, think about 20 watt light bulb, 50 watt light bulb. 50 watt light bulb way brighter than a 20 watt light bulb is, so there's more available power. This can supply 50 watts of power, whereas the original one only could supply 20 watts of power. So here was my idea, my concept. If you bought an 18 volt transformer, you know it's going to put out 20 plus 20 point something volts, because that's sort of a standard for that type of transformer. If you buy a transformer that puts out 20 volts free running and you have enough extra watts, you have 50 watts. 50 watts is this huge bowl of available power. It's 50 watts of power in the bowl. The door chime is only going to use a small part of that. So in theory, the voltage that comes out of the transformer, the 20 or so free running volts, it's not going to drop very much, because the transformer is having a really easy time keeping up with the demand that the door chime's putting on it. See, this has way more power than it needs to have, so this can have the power it wants, and it doesn't affect this very much. So let's see if I'm right. Let's see if what I think works out. So here's our setup. We have our K model chime here. It's wired up on a single standard push button for activation. Here's our MG Electronics transformer. I have it right now wired up. I'm going to change this configuration because I was measuring amps, not volts. So I'm going to change this around. This is just plugged into an extension cord right now because it's easier to show you than if I plug it in the wall over there. And so I'm going to go ahead and plug this in. I'm going to change the wires around, plug this in on the wall, and I'm going to show you on the meter how many volts it actually puts out. Okay, so you're looking at the display on my bench multimeter. Our transformer is plugged in, so it's powered up. Oh, by the way, I have this discussion with people all the time. These type of transformers, doorbell transformers, these are AC transformers. These are not DC transformers. They're AC. So when you measure them, you have to measure them on AC voltage on your meter. Otherwise, you don't get the proper reading. The chime's not running, the transformer's powered up, and if we measure it, we get 19.9-ish volts. Now, how many volts actually come out of it depend entirely on how many volts are going into it. So in our area, the voltage that comes into the building will change as the day goes along. In the afternoon, it's usually less. In the morning, it's usually more, based on demand in the area and all those kind of things. But give or take, in round numbers, it's putting out 20 volts. It's close enough. So now what we're going to do is I'm going to change it around. I'm going to change the setup around, and now we're going to measure how many watts or how many amps the chime uses when it operates. I changed my setup around. You'll notice that the red probe it was plugged in up here before. Now it's down here at the bottom because we're measuring current, and we're on AC current, not DC current, AC current. Current is watts, amps, milliamps, things like that. It's the amount of power that is flowing through the meter, which is being pulled through it by the device. So right now it's usually almost nothing. I'm going to push the button on the chime, and you're going to see the numbers change. And as the chime shuts off, it will go back to almost zero. All right, so let's do that again. This time, since that was the first time you saw it, what you're looking for is the highest number that you see after the decimal point. And that number will be the combination of the power the chime is using with the motor running, so it's power to power the motor, and also power to power the solenoids each time it strikes a tube. And that's why the numbers fluctuate up and down, because when it strikes a tube, it uses more power, and then the motor continues to rotate, and then it strikes the next one, and so on. So the numbers go up and down, up and down, up and down. And now, while it's coming to the stop point, it's using 0.3 of an amp, 1/3 of 1 amp. You saw the numbers go as high as 0.7, I think 65 or 1.2, 6.9, you know, it goes up and down. It's a mechanical device and it will vary somewhat from solenoid to solenoid. Now we know that the chime at the most draws about 3/4 of 1 amp. So now what we're going to do is we're going to change the setup back again to measure voltage. And I'm going to measure the voltage coming out of the transformer while the chime is running. And what that's going to show us is, it's going to show us how much the output voltage of the transformer sags as the demand on the transformer increases while the motor is running and the solenoids are striking. All right, I've changed my setup back. We're now back on the top input, which is for volts. We're on AC voltage here. And I'm going to connect the probes of the meter to the output of the transformer. And now we're at 20.1 volts because, as I said, as the input voltage into the shop varies, the voltage coming out of the transformer will vary. So obviously our line voltage has increased a little bit. Maybe all the neighbors have turned off their air conditioning. Now I'm going to push the button to run the chime and we're going to see how the numbers fluctuate. And as you saw, the voltage dropped a little, but not very significantly. So right now, what would be our free running voltage is 20.1 volts AC. And now I'm going to push it, and what you're going to see, it's going to be very similar to when we were measuring watts. When the motor starts to turn, the voltage is going to drop a little bit. When each solenoid is energized and the plunger fires out of it, it's going to drop more, and then it's going to go back up while the motor runs to the next point, and then at the end, when it's running after the 8th note is rung and it's running to the stop position, the voltage is just going to be based on the amount that the motor is using as it runs to the end point. So here we go. And now it's running to the end point. So while just the motor is running, the voltage dropped to 19.8. Okay, so what does all this prove? Why do you care? Well, what this proves is my theory is mostly correct. This 18-volt transformer that has a free running voltage of right around 20, but a huge power capacity of 50 watts, the voltage doesn't sag barely at all. And with just the motor running on its own and the solenoids not being energized, it's nearly 20 volts, which is actually nearly ideal. So what this all proves is this transformer is a reasonable substitute for an original NuTone transformer that a lot of people don't have anymore. It's gone missing, it was taken out, it wasn't taken out when the chime was removed from the original house or whatever the deal is. The nice thing about these are, you can buy these online. These are commonly available in a lot of places. These will cost you about 20 bucks. And that's pretty reasonable. That's way, way, way better than paying me a couple $100 to build a transformer appliance. So at 20 bucks, it's a no-brainer. This is a good choice. And I don't think that little bit of 1/4 of a volt or 1/2 of a volt less, it's not going to make any difference to this. This has plenty of power, and really, in some respects, the power, the amount of available power, those 50 watts, is actually sometimes more important than the voltage, as long as it's not too high, because you don't want to damage the motor, because when the solenoids strike, they need a lot of power. They want a lot of power, so they strike well, and then you can use the volume adjustment to change that. One of the nice things about this transformer is, like all things nowadays, it's got a wanky little green LED light on it to show you that there's power in the socket where it's plugged in. But there's one other thing about this transformer that you got to know, because there's something else you got to do to make sure it lasts for a really long time. I've disconnected everything and moved it all out of the way. One of the things you have to know about these kind of transformers is because of their size and because it's more of a consumer-y kind of product, built inside of them is a fuse. And it's not a replaceable fuse. It's built into the unit. This is all sealed up, and there is no way to take it apart, and there is no way to break it open to replace the fuse if it blows out. The fuse prevents the transformer from being overloaded. If you connected some device to it that requires too much power, or that device has a serious problem and you didn't have a fuse, this thing could go up in smoke, and that wouldn't be safe, so they put a fuse inside of it. That can be a problem, because one, the door chimes can occasionally, especially when they're really old and really tired, they can create a problem where they get stuck and the solenoid stays on forever and it draws too much power, and that could in theory blow the fuse in the transformer. The other thing, which is a realistic problem, is that a lot of people that are doing this is the first, last, and only time they're ever going to wire up a door chime. They're not really door chime experts, and when you're hooking up wires to this and you're hooking up the wires at the other end, if you're not 100% sure what you're doing, you might hook it up wrong, you'll have a short, and it'll blow the fuse, and the transformer then becomes a brick. It's not repairable, and your 20 bucks is down the drain. And that's not good. I don't like that idea. So what I decided to do is I put a little fuse on the transformer. And all I did was I bought an inexpensive fuse holder, and it's a really simple one, because this does not require anything really fancy. All it is a little, you unscrew it, and inside is a little tiny AG2 fuse. And it's connected to one side on one output connection of the transformer, which is all you need. You don't put two fuses, one on each, you only put one fuse. You screw it back together, and now the fuse protects basically the fuse inside the transformer. How do you know what size fuse to use? Well, this transformer has the capacity, and you can't find this out specifically because the manufacturer doesn't really publish it, but if you calculate out the numbers, this transformer, this one specifically, can supply up to 2.5 amps of power. And there's a simple calculation that you do to calculate based on the volts and the watts to come up with the maximum amount of power it can put out. If this can put out 2.5 amps, odds are the fuse that's inside of it is rated for something right around 2.5 amps, because that just makes sense. So since we want to, the point of this fuse is to protect the fuse that's built into it, this fuse has to be smaller, lower rating than the one that's inside, because you want this one to blow first, not that one. And because this one is replaceable. So what I chose was, and I had to choose this when I was making a parts order before I had one of these to test with, so there was a little bit of reasonable guessing, and what I guessed was that a 2 amp fuse in here would be the right choice. And this is a 2 amp, it's called a fast acting fuse. It's a quick blow fuse. It's not a slow blow fuse where you get 8 or 10 seconds of overload before it fries. This is like you have a short, poof, it's gone that fast. It's in an instant, it's gone. Because really that's what you want. You want one that's going to blow quickly, because you don't want to blow the one in here because you can't fix that one. So I chose a 2 amp fuse. Now that we know that the chime in really good condition draws 3/4 of an amp, it would also be reasonable. This one probably could be dropped down to 1.5 amps, but that little bit of difference isn't going to make much difference. If you have a really serious failure or a really serious short, it's going to blow instantly. If I hooked this up deliberately and shorted it, this fuse would go pop, and it would just in an instant. So it doesn't really make any difference. So if you're going to do something like this, you need to do something like this to go with it, because otherwise this could turn into a brick. That was my genius idea. An inexpensive way that customers with K-model chimes that need a 20-volt transformer can easily come up with something like this that doesn't cost a lot of money at all. 20 bucks is pretty reasonable for a transformer. You do have to do something with the fuses. This might be something that we have available for people that send us chimes and something. Not really going to sell transformers, because if I have to buy these for 20, I can't just sell them for 20. It's too involved to do that. But we might have the fuse link assembly as something we can send back with people's chimes after we've repaired them, because that makes it easier for people. All I did on this to make sure the connection was good and will last forever, I just put a little eyelet connector on it and soldered it on. My crimper is at the shop, so I couldn't crimp it, but I'll probably do that also. But I soldered it on so the lug will stay on there, and then you just take the screw out and then you put it back in place, and that's really all you got to do. And and for those of you who might ask, yes, in theory, you could put the fuse here in the chime if you wanted to, instead of on the transformer. But I think personally it belongs here on the transformer, because if it ever did blow, or if you ever did have to replace the fuse, it's much easier to go out to your garage or your furnace area or wherever the transformer is located and do this right there, instead of having to take the cover off the chime and you got to try to fit it all in here and keep it out of the way. It's just simpler to put it in here. So that's what I would recommend. I hope you found this interesting, and maybe for some of you it will be helpful. If it is, give it a thumbs up on YouTube, because that helps us just a little bit. There'll be a banner right here that shows you how to subscribe. Go to our YouTube homepage, click on the bell, and when you click on the bell, click on it to receive all notifications, and every time we post a new video, you'll get a notification and you can watch it. That's all for today. See you on the next video.